I think he's
March 22nd was the last time something.
Okay.
Or not?
All right, John, it's
Yeah.
your job to just move that chair out of the way so no one sits in front of
There
you.
won't be a morning today.
I know he's not here.
That's for sure.
No, he's not, so we'll have a microphone, it might be great. Just put your feet up on it and
I'm gonna try and look as leisurely
I
as
could just sit,
possible.
I could just sit next to you.
You could do that.
Sit in the front row.
Yeah, because usually somebody's sitting next to you because you're so popular.
No, just because I'm blind. That's why I'm. So, I'm sorry we got that honey about we got to go for dinner. We just, last week was the break and this week I was out of town in the middle of the week, so we'll get back to that. So, love you. I'm sorry about that.
Actually, I don't have the one outside since I came in. I periodically forget as well.
But you guys aren't nervous about being inside, right?
No.
Oh,
We're on the road. If we were nervous, I would just tell you that we're
okay.
So no, that's about it.
This is Hannah, who is our resident faculty member interested in exoplanets.
Hello.
It's on exoplanet hiring.
Yes.
Oh, what area are you of exoplanets are you interested in?
I want to do icy worlds oceanography, more like icy worlds.
Oh yeah, no, actually, this is
Yeah,
right up
I'm
your alley.
excited for
Yeah,
this.
yeah. If you've been thinking about Hycean worlds, then well, that's what we're into there. But yeah, the icy world stuff, as well as snowball stuff. I'm not talking about that thing, the ice worlds and snowball stuff.
You overlap with Malta, yeah, is that right?
I never wrote anything with Malta,
Okay,
but I used to be in the same department.
Yeah, right.
Yeah, he came into Chicago just about when I.
Right. Yeah, I wasn't sure that I know, so yeah, he's been thinking a lot about that stuff.
Oh, has he actually?
He's been thinking more on that, yeah, because there were a couple ocean sciences sessions a couple weeks ago, and he gave a talk during that, kind of thinking about energetic constraints and some of the icy world stuff. So.
Yeah, because Ellie Zimmerman did some really interesting work on oceanic and
Yeah, a lot of cool stuff.
More faculty members. That's on hell back there.
Well, there's my person. Because John asked me where he was, I was like, I don't know.
Dynamics that are unique to moisture influencing convection.
Oh, okay, yes.
The mid-tropospheric moisture influencing convection. So we were just talking about the kind of dynamics that come out of that.
What is
He's not my student, no, he's a faculty member.
It's harder.
No, I wasn't here.
Sorry, I should have specified that.
But I'm going to Puerto Rico like in a couple of weeks. My brother's getting married, so one of my brothers.
Okay, well, I think we should probably get started. So hi everyone, thanks for making it out for the special colloquium on relatively short notice. So it's my pleasure to introduce Ray Pierrehumbert, who he is the Haley Professor of Physics at Oxford. That's his current position, and he has worked on just a huge range of different problems over the course of his career, ranging from dry dynamics to climate, snowball Earth, and most recently exoplanets. He's gotten into all sorts of exoplanet work, although he still has some climate work going on as well. And so he makes use a lot of kind of the basic physics that go into atmospheric science and applying that to all sorts of different problems, including in this case, these temperate subNeptunes. So.
Yeah, well, thank you very much. It's a pleasure to be here. For various other reasons, I was coming to Chicago and Madison, and it would be silly to be here just down the road and not drop in. So I am very pleased it was possible to arrange this impromptu seminar. I have lots of reasons for being around here, so I'm sure you'll see more of me. I think this is the fourth time I've been at Madison to give a talk. Some of those times have been over at Applied Math and so forth. I've talked about various other things, but as Larissa said, one of the nice things about the universality of physics, of planetary physics, is that the same kinds of processes that you learn about by studying the Earth really make use of the very same physics that would apply to quite different worlds if you just tweak what the latent heat of the condensable is doing, or change the boundary conditions at the bottom. You have a mostly gassy planet versus a planet with a solid surface, and something like that. And actually, one of the things that actually brought me to Chicago on this trip was the American Physical Society meeting, when we had a special session on the Nobel Prizes, which was a great thing that Suki Manabe got a Nobel Prize for physics. And in that talk, I pulled out a quote from the Feynman Lectures of Physics, which Feynman actually has a chapter on fluid dynamics, the Feynman lecture, where he points out we don't have a way of teasing out qualitative behavior like vortex streets and convective fluids and things like that from the basic equations of physics. He used planetary physics as an example. They only had the solar system planets at the time, but pointing out how the same building blocks in physics, put together in slightly different ways to a huge diversity of different climates. And then that's just amplified, we've just broken the 5,000 planet barrier in terms of how many exoplanets we know, and it just, the range keeps expanding, but it's still the same basic building blocks in fluid dynamics, thermodynamics, radiative transfer, and a certain amount of chemistry. So I'm going to talk about subNeptunes. I'll tell you soon what a subNeptune is. These are maybe the most common kind of planet in the universe. And first I want to plug a book. Actually, you can plug two books. So I'm working on the second edition of Principles of Planetary Climate now. And there's been, in the 11 years since that first came out, or since I first sent it to the press, there's just been an explosion of new information about exoplanets. So it's going to be very extensively revised and all built around Jupyter notebooks, which make it much easier to do supplementary materials. But I have a little book that has come out on something that I wanted to learn about. So I thought I'd write this book to actually get the bigger picture. So this is about planetary systems, about generalizations of the notion of the solar system. It's what it's things like the solar system. It turns out it's actually pretty hard to make a star without also making planets. So this book sort of goes from the collapse of giant molecular clouds to protoplanetary disks, the birth of stars, and what determines the composition of planets, and also the habitability. But my favorite chapter is the last one about how everything ends, the two different pathways by which planetary systems die. It's written for a general audience, but I tried to make it as quantitative as possible, being a very short introduction series. It's a quick read, but if you want to, if you're an expert on this, there's no point in looking at this book. But if you want to learn something about where planets come from and where they go, I recommend it. It makes a great birthday present or Christmas present. So about subNeptunes, I'm going to talk about the definition of subNeptunes and their possible compositions, and then spend some time talking about the 1D structure, which involves some interesting thermodynamics, and then get to the stuff that will probably appeal to this audience most, which is the kind of atmospheric circulations of subNeptunes. And there's some very deep analogies, or some deep analogies with tropical meteorology that will come in the understanding of these atmospheric circulations. Planets in some ways have a circulation that's a lot like an all tropics planet. I'll give some dry general circulation model results of subNeptunes, and then we have some preliminary results on moist circulations. So what is a subNeptune? It's a smallish planet, and there's no strict boundary, but think of it in something like planets roughly less than 2 Earth radii. But what makes it a subNeptune is that the volatile envelope, which is an atmosphere, ocean, or ice, some low molecular weight thing, the volatile envelope makes up a substantial fraction of the mass. The atmosphere could be hydrogen. And if you have a hydrogen atmosphere, since hydrogen has a very large scale height because it has a low molecular weight, it doesn't take a lot of mass of hydrogen to puff up the radius of a planet quite a lot. So you can reduce the mean density of a planet quite a lot by having a hydrogen envelope. You need, if you're actually making the planet have low density, so that the volatile envelope is a substantial part of the mass of the planet. If you're doing that with, say, water ice, then you practically need to make the whole planet out of water ice in order to get the observed densities of these planets. Okay, but anyway, it's a situation where the density is too low for the planet to have a dominant rock-iron composition. And Venus, which some people think of as having a thick atmosphere, Venus, the mass of the Venus atmosphere is only about 2.02% of the mass of the whole planet. So Venus would still count as a rocky planet. That's not. So these things are more like Neptune or Uranus, but small. That's how you think of them. And I'll talk about what they might actually be made of. Actually, in terms of the volatile envelope, Earth actually has, if you count the ocean, and an ocean is really just like a dense kind of atmosphere. If you count the ocean, Earth actually has a more massive volatile envelope than Venus, but it's still down in the fractions of a %. These planets are so new in terms of people thinking about them. The notion of what you should even call them hasn't completely settled down. I started off calling them gas midgets as opposed to gas giants. The first one we discovered was a planet called GJ1214b, which has a mean density about twice the density of water, which is about what you would get if you made a whole planet out of water and squeezed it by gravity. Some people have been calling them Neptinos or Neptunes or Neptinis. I'm trying to push in the word Neptini these days because it's teeny. It's like a teeny Neptune. It also sounds like a great name for a drink.
Yeah, it sure does.
Yeah, would you like a Neptini? They don't necessarily have the same composition or structure as Uranus or Neptune. And something I was surprised to find once I started looking into this is that we don't actually even know what the dominant composition of Uranus or Neptune actually is. They're called ice giants mainly because they're out in a part of the solar system where the dominant thing you would expect to make them out of would be various icy substances. It doesn't mean that it's actually mostly ice, but you can actually match. We can only directly observe the outer atmosphere of Uranus and Neptune, which is dominantly hydrogen with traces of other things. But you can actually match a lot of the characteristics of Uranus and Neptune by having a big rocky core and a hydrogen envelope. Or they could be predominantly made out of ice, out of like water ice and contaminated with other ices with a smaller hydrogen envelope. And there are some indirect chemical amateur chemistry inferences that push you a little bit in the direction of having an icy internal structure rather than a rocky internal structure. But what you really need is something like a Juno mission to Uranus or Neptune to determine the interior structure. But in this talk, I'm going to pretend that these are ice giants and have a dominant icy composition, but there could be surprises off in the future. Okay, so, by population statistics, subNeptunes are probably the most common kind of planet in the whole universe. And I'll give you a few examples of some interesting ones, and I'll show you a scatter plot with how many of these there are. Okay, so this is, so the first one, as I mentioned, was GJ1214b. It was discovered by Dave Charbonneau's MERTH project, MERTH. 2.7 Earth radii, 8 Earth masses, and 0.4 times the density, 0.4 times the density of the Earth. It's in a short period orbit around an M star, a low mass star. But it's so close. Even though these low mass stars are much less luminous than the sun, it's receiving 20 times the stellar flux as the Earth, so it's very highly irradiated. The black body equivalent equilibrium temperature is 600 Kelvin, which can be thought of as the temperature of the photosphere, the radiating level of the planet. And the rest of the planet you get the temperature of by sort of extrapolating along a kind of adiabat. But this is so hot that the water vapor, if it's there, would never condense. There's no place in this atmosphere where water vapor would actually condense, although in the interior you could have high pressure hot ice phases. But you wouldn't have conventional Earth-like water vapor clouds here. The dominant clouds would be things like zinc sulfide and potassium chloride. And it has, it's the spectrum, the transmission spectrum of its outer atmosphere has been measured astronomically, and it's completely flat in Hubble, which means that it must have a thick, high cloud deck, or be made out of a high molecular weight thing like CO2. And we're all looking forward to the James Webb observations of this, which can look into where gases have better absorption features, and then you might be able to see above the cloud deck and see what's in the atmosphere. We have no direct evidence because of this very flat spectrum of what the atmospheric composition of this planet is. This is an interesting case where we do know more about the atmosphere. Discovered about a little more than a year ago, maybe 2 years ago now, I guess. K2-18b, it's from the extended mission of Kepler. At about 2.4 Earth radii, almost 9 Earth masses. This is a somewhat higher density thing, which would indicate a more substantial rocky core, but it's still only 0.67 times the density of the Earth, which requires that it has a very substantial volatile envelope. This will be important when we get back to the dynamics. There's about a 30-day period. It's also around an M star, but it's farther out. Longer period means farther out. So it's getting an installation, an amount of stellar flux that is almost this. It's just a little bit more than what Earth gets. So this is an example of a temperate subNeptune, in the sense that this could have Earth-like water clouds. And what's more, we do know two things from the transmission spectrum of the atmosphere, from what parts of the starlight are blocked when the planet passes in front of the star. This definitely has a hydrogen-helium dominated atmosphere, and there's a tentative detection of water vapor in its atmosphere. And so this is an interesting case of water vapor possibly condensing in a hydrogen atmosphere, which is really dynamically interesting. We'll come back to this. It's dynamically interesting from this as a counterpoint to Earth moist thermodynamics, Earth moist convection, that on the Earth, water vapor is buoyant relative to air, 18 versus 29. 18 for water vapor, 29 for the background molecular weight. But water vapor in a hydrogen atmosphere, hydrogen is 2, it sinks like a lead balloon. It enormously stabilizes the atmosphere against convection. And so you need to build up a huge amount of CAPE before you trigger convection at all. It's one of the things we're working on. But it also has dynamical effects through a very, very strong virtual temperature effect of water vapor there. This is another recently observed planet. We don't know for sure that it's a subNeptune because we don't have mass. We have the error bars and the mass estimates are very large. It's on the borderline of the radius where things tend to be low density rather than rocky planets. It's in an 18-day period. And this is only getting twice the installation, twice the stellar flux as Earth gets. So it's still hot. It would be if it were a rocky planet, this would be in the Runaway Greenhouse zone where you couldn't have a liquid water ocean. And I'll get to what it would mean for a subNeptune to be in a Runaway Greenhouse state. And it's also around an M star, a low mass star, red dwarf star with a photospheric temperature of 3,600 Kelvin. And then this is the most recently determined one that I know of, that, or at least well, I haven't checked yesterday. There are new ones coming in every day, but this is a really, really fascinating case. This is from the TESS mission, TESS Object of Interest 2257b. It's about 2.4 Earth radii. We don't know the mass. There hasn't been a measurement of the mass of this yet because it was detected by the transit method, which just gives you, if you only have one planet, it just gives you the size of the planet, not the mass. But from population statistics, when you get into a radius range like 2.37 Earth radii, most of those do tend to be low density things. Whereas you get much below 1.5 Earth radii, they tend to have high density and be rocky. So again, this is this is in a long period orbit, a 35-day period, but it has an eccentricity of almost 0.5. Extremely eccentric orbit, which should give it some really fascinating dynamics, because there's a huge seasonal cycle. It will have a huge distance-induced seasonal cycle. The mean installation is sort of Mars-like. The mean installation averaged over a time average of the orbit is 0.7 times the Earth's installation. Giving it a, if it has 0 albedo, it would have a 253 Kelvin temperature. It almost certainly has an albedo more like 0.2 or 0.3. And it's also around a low mass star or red dwarf star. But because of its very eccentric orbit, the installation when its closest approach is twice Earth's installation, but it goes down to a quarter of Earth's installation at its farthest distance. So this will be very exciting from the standpoint of transient cloud effect, because if there's water vapor in its atmosphere, when you're close in, you actually will dissipate. It will heat up so much you'll dissipate clouds, just about any clouds in the observable part of the atmosphere. But then all of that will snow out or rain out as you go to the farthest point. So we're working on modeling. I won't show you any models of this yet, but we're working on modeling that, because if it's a hydrogen atmosphere with clouds, for example, or any kind of atmosphere with water vapor in it, it's going to have really interesting transient dynamics, which will give us a unique window into the nature of the atmosphere. So these are just a handful of several hundred, maybe actually several thousand subNeptunes. So what might a subNeptune be made of? For the most part, we know the two things we generally can tell about many subNeptunes is we can tell the composition of the outer atmosphere, because all the astronomical methods probe just the outer few scale heights of the atmosphere. So that's not necessarily representative of the composition of the whole planet. And the other thing we know, if we're lucky, we have both the mass and the radius, and then we can get the mean density. And mean density is what mostly classifies things as a subNeptune or not. But you could have a state which is has which is a bit like an ice giant. It's basically an ice ball. You could have a planet which has very little silicate rock core and very little nickel metallic core, but is mostly made of some high pressure phase of liquid or ice, which I'll get to shortly. You could have an Earth-like water ocean, liquid water ocean, above that, and then possibly you could have a regular ice run, low pressure ice crust above that, like a snowball Earth, and then a high molecular weight atmosphere like nitrogen, carbon dioxide, or something like that, which is a fairly thin part. But here you're relying on the low density of these liquids and ices in order to make it low. You could also have a situation where you could have a situation, and this is getting to be in the category of what some people are calling Hycean worlds. You could have a situation where the low density is not just due to the ice. You could the ice composition. You could have an extended hydrogen-helium atmosphere. And if it's hot enough, if this is thick enough, you wouldn't have the ice crust, you would just have the hydrogen-helium atmosphere over a water ocean, and that's what I think people are mostly thinking of when they talk about Hycean worlds. Now it's another model of habitability. And it's an alternate model of a habitable planet because you can have life in a water ocean. But it's also, these are also attracting some attention in terms of possible cloud life. Because even if down here the situation, the temperature and what have you, is not suitable for life as we know it, there could be a habitable zone where you have liquid water somewhere in this hydrogen and helium atmosphere. Sarah Seeger has been looking at various ways you can make that happen. In fact, there has been thinking and possible biosignatures regarding cloud life on Venus. The actual detection of phosphine on Venus, which was supposed to be a biosignature, is now viewed as very, very dubious. But Venus does have a layer where you have liquid water in the upper atmosphere and Earth-like temperatures. And so we have bacteria that live in clouds on Earth. So if there is some way that life evolved in Venus and migrated into the clouds, it's not a crazy idea. What makes it difficult on Venus is that the clouds are extremely concentrated sulfuric acid with very low water activity. So it's hard for any kind of organic thing to survive there. But these kinds of Hycean worlds don't necessarily have that problem. In fact, if they're mostly icy, they probably don't outgas sulfur dioxide. And without the sulfur dioxide outgassing, you don't make sulfuric acid. So there's a lot of interest in these as possible ways of making cloud ice. Another thing you could have you could have a planet that's just a water world, where you don't go through the phase transition to high pressure ice phases. Instead, you have a water vapor atmosphere, and then you go to this is what GJ 1214b would be like if it indeed is mostly made out of water. You have a water vapor atmosphere at low pressures, but you would go past the critical point of water. You would never cross the phase transition from gas to liquid water. You would be supercritical all the way down, and so you just smoothly go from a gas-like thing to a liquid-like thing without ever passing a phase boundary. Just like hydrogen goes from a gas-like thing high up in Jupiter's atmosphere to a liquid-like thing without ever going through a phase transition as you go to higher pressure, because hydrogen is supercritical with regard to the liquid-gas phase transition all the way through. For a hot planet like 1214b, this is the situation you would have. Whereas for like K218b, which is colder, these other cases with high pressure ice phases or liquid phases in the interior with phase transitions and phase boundaries. Okay, and there you could have a situation where you had much less, where you had a bigger rocky core, possibly a water ocean, and then you made the density low by having a very extended hydrogen-helium atmosphere. This is also a Hycean world. And that contrasts with the Earth-like case where most of the planet is a silicate mantle and an iron, a metallic core, and a low-mass ocean and a low-mass atmosphere. But all of these things, and I haven't even rung all the changes and the possibilities of structure. All of those things can match the density ranges of subNeptunes. We will get more information about the composition of the outer atmosphere. It's really not clear what pathway there is to actually, for exoplanets, figuring out what the internal structure is. Now, in terms of Hycean worlds, this is from a paper that my postdoc, Shamit Said, published not too long ago. With regard to, there was a lot of question on a K218b, which we know has a hydrogen-dominated outer atmosphere. There was some question about whether it has a deep hydrogen atmosphere over a liquid water ocean, or whether it has a shallow hydrogen atmosphere and then a deeper ocean making up its low density. We figured unless there's unusually reflective clouds that do not have much greenhouse effect, we found that actually there was no solution in which you could actually have hydrogen over a liquid ocean. And the reason, these are radiative convective models with different metallicities, different amounts of non-hydrogen helium stuff in the atmosphere. No, sorry, this is all, sorry, this graph is all 100 times solar metallicity, 100 times the amount of non-hydrogen helium contaminants that you get in solar composition. And we've done this for other metallicities too. This is just radiative convective. This is the pressure going down to 100 bars, the different curves here are putting the bottom of the atmosphere, the bottom of the hydrogen helium atmosphere at different pressures. Like this curve is a thin atmosphere, just 10 to the minus 2 bars, with and then surface underneath that. But the main thing to look at here is if you have even a 1 bar hydrogen atmosphere, you have even a 1 bar hydrogen atmosphere for K2-18b. The temperature you get just from radiative convective equilibrium is supercritical with respect to water. It's a supercritical temperature. And so actually, if you tried to put a water ocean even at the bottom of a 1 bar hydrogen atmosphere on K2-18b, the water ocean would not, it would not have a distinct density jump. It would be supercritical water, not liquid water. And supercritical fluids are miscible, infinitely miscible with other gases. So your 1 bar hydrogen atmosphere is completely miscible with your ocean. You're not limited by Henry's law anymore. It's completely miscible. The hydrogen would just get diluted into your massive ocean. And so you wouldn't see hydrogen out there. And so, and that's just with 1 bar. If you go to say, 100 bar hydrogen atmosphere, you're even hotter. So K2-18b is just too illuminated to actually have a water ocean. Unless you have, there's a way out if you can cook up some kind of cloud that increases the reflectivity without excessively increasing the greenhouse effect, the cloud infrared opacity. You might be able to give it a water ocean, but it's a kind of a stretch for K2-18b. If you had one of these that's a little bit farther out, then you could actually, hit the threshold where you could have 1 bar or 10 bars of hydrogen, over a water ocean. So I already said that verbally. Okay. Now, what is the interior state? What is the interior state of water substance? Let's go to the case where a completely water-dominated planet with maybe a small silicate core, silicate and iron core in the center. What phase are we actually talking about? So this is the phase diagram for water that goes up to the critical point. Here's the critical point. This is temperature on the horizontal axis. It's pressure on the vertical axis. If I flipped it over vertically, this would be like a vertical sounding of pressure and temperature. This is the top of the atmosphere at low pressure. This is the bottom of the atmosphere deep in the planet. And that's 1 terapascal, 100 gigapascals. And so actually, so a planet will if it's got a convective layer, the temperature pressure trajectory will be something like this. You go to higher temperatures as you go into the interior if you're following along an adiabat, for example. Even if you start at a cold temperature, we're at a fairly cold temperature, and you start to go into the interior. If you're cold enough that you cross this phase boundary from water vapor into liquid water, first you go to liquid water, then you can have an ocean. But then as you go into the interior at higher pressures and temperatures, that's 100 kilobars, you hit the ice phase in the interior. But it's not familiar ice 1. It's not your regular ice 1, which is the ice we all know and love and put in our drinks. And of course sea ice and glaciers and what have you. It's these high density, high temperature ice phases, ice 7 or ice 6, depending on exactly where you are in this diagram. But actually, the interior, even for Uranus and Neptune, the interior is too hot to actually. The interior is too hot for the interior to be ice 7, one of those high pressure ice phases. And there's been some really interesting, recent work using ramped heated shocks at the National Ignition Facility, the laser fusion place that some of my colleagues have done, compressing water to very high pressures and temperatures. And so this is an adiabat. This is an adiabat for Uranus, starting from the upper atmosphere temperature of Uranus. Now has the pressure and temperature flipped around. The pressure is on this axis, the temperature is on this axis. And so that's 10 gigapascal, which is already, deep, fairly deep into the planet. But this adiabat is extrapolated from the upper atmosphere temperature of Uranus. And so down here are there's ice 7 down in that little corner there. Even for Uranus, which is starting off pretty cold, the adiabat you go on is just, stays above the ice 7 phase transition. And so the actual interior structure is not an ice at all for most of it. It's an ionic fluid for part of it, which is a fluid. It's water, but where the positive and negative charges have separated out, so it's weakly electrically conducting. But that was known for a long time. So there was the question: was there some kind of ice phase in the interior? So down here there is an ice 8 phase, which is a solid ice, and it's not electrically conducting. But they discovered this really interesting superionic ice phase, which is an ice, but with mobile ions in it. So it has a crystal structure, but it has mobile ions in it. So it's electrically conducting, and so it can support the generation of a magnetic field. This phase has been confirmed in actual experiments. The pressure, since SubNeptune is a smaller planet than Uranus or Neptune, you don't go all the way up to 500 gigapascals towards the center like you do on Uranus or Neptune. The interior pressure in a SubNeptune is more like 200 gigapascals. So you cut off this diagram at sort of here. But you are starting from a hotter adiabat because these things are closer in. And so it's actually the interior structure of SubNeptune that's dominantly made of water is probably mostly in the ionic phase or the conducting fluid phase. There's a conducting fluid phase up here, and it's unlikely that you would get into the superionic ice phase. So it's mostly a fluid planet, but with electrical conductivity as you go into the interior. Now I am working. It's really hard to do these non-ideal adiabats, non-ideal gas adiabats, and I'm trying to get a handle on tabulated computations of the internal energy, so I can actually compute those adiabats for subNeptunes, and we're not there yet. I have to learn a lot more about non-ideal gas dynamics and get the internal energy as a function of pressure and temperature. One of the challenges for a non-ideal gas, unlike an ideal gas that we all know and love, the internal energy is not just C sub PT anymore. The internal energy is a rather complicated function of both pressure and temperature. And so you need two-dimensional thermodynamic data to determine an adiabat. And the computation is not hard, but getting your hands on that internal energy data is pretty hard. Now actually, I'll go through this very quickly, and then I'll go through the runaway stuff very quickly. I'll spend the last 15 minutes talking about the dynamics, dynamical things. A runaway greenhouse state, which is how we think Venus got to where it is, comes about when the water vapor, when you get warm enough, the water vapor opacity dominates the opacity of the atmosphere. But now when water vapor dominates the upper atmosphere, if it's saturated, the temperature is determined by pressure. It's just the dew point. So the adiabat has no free parameters anymore, which means that when you heat up the planet, you add more mass to the bottom by evaporating the ocean. You add more mass to the atmosphere. But you don't change the temperature of the part of the atmosphere that's radiating to space, which means that while you still have an ocean to feed the atmosphere, you can never increase the radiation to space. So if you have too much absorbed solar radiation, the planet will heat up until the whole ocean has been used up. And at some point after that, the OLR can start going up again. And so that's the runaway greenhouse. There's a threshold there, and so this just if you just look at this, right, this is a pressure temperature diagram after the ocean has been completely evaporated, and these are different surface temperatures. And so this line here is the dew point adiabat. It's just gotten by solving Clausius-Clapeyron for temperature in terms of pressure. So it's just an ordinary dew point that you all know and love. And so after the ocean has evaporated, then the lower atmosphere is subsaturated, so you're on the dry H2O adiabat, the non-condensing H2O adiabat. Then you encounter the condensation point. After that, you're stuck on this dew point adiabat. The hotter it gets, the farther up the condensing level is, and so eventually this region where the temperature goes up with the surface temperature eats so far into the upper atmosphere that it's optically thin and you can start radiating more again. But that only happens after you run out of ocean. This is what happens on a terrestrial planet with sort of an essentially finite mass ocean. This is what the OLR actually looks like from our calculation. The outgoing long-wave radiation as a function of surface temperature this is with a 260 bar ocean. It goes up for a while you still have an ocean, then it's flat. That's the famous Kobayashi, Ingersoll, Simpson, Nakajima limit. People keep adding more names to that discovery, but and then at some point, long after the ocean has been used up, that the condensing layer retreats to high enough in the atmosphere that the OLR can start to go up again. And then, say if your installation was at say 1,000 watts per square meter, your absorbed solar radiation rather was at 1,000, then you would equilibrate at a temperature of about 1,500 Kelvin. So typically, if you have an appreciable, well, actually that's with a 10 bar ocean. With an Earth-like ocean, you're equilibrated at a temperature of over 2,000 Kelvin. That's why post-runaway atmospheres tend to make a magma ocean underneath the water vapor, because most rocks melt at 2,500 Kelvin. So runaway greenhouse and magma oceans go together, and that has really interesting geochemical consequences. But this is for a terrestrial planet where you've got like 200 bars of ocean. You can run out of ocean, it all goes into the atmosphere, and then you can equilibrate again. But what actually happens if you have a subNeptune, which is all made out of water? You can't run out of ocean because the whole planet is ocean. So you can't equilibrate this way. So how does it actually equilibrate if you're in a runaway greenhouse situation? Okay. And the answer is actually the runaway greenhouse. You can't run out of ocean, but what happens instead is that what would have been your ocean goes supercritical, and then the adiabat is connected to the deep atmospheric temperature, and so the whole deep planetary temperature warms up until you warm up the upper atmosphere to the point where you can radiate again. And so what's going on in that top 100 millibars of the atmosphere is controlling the temperature of the whole planet right down into the interior. But to figure out what the temperature is in the interior and what the phase is, we have to be able to compute that adiabat, which I don't know how to do yet. I mean, I sort of know how to do it, but I don't have the internal energy data to do it. But so that is what, runaway greenhouse is still a significant concept for subNeptunes. It's just that unlike the situation on a rocky planet where you run out of ocean and then you get a magma ocean, it is determining the interior temperature of your whole planet, which determines what phase the planet is, what phase the interior of the planet is. Okay.
Does Venus have a magma?
Sorry?
Does Venus have a magma ocean?
Not anymore. If Venus had water, now there's some indications from really incredibly interesting recent modeling, there's some indications that Venus could have lost its water before it ever cooled off enough to have an ocean. But if Venus started off with an Earth-like ocean and then lost it to space through a runaway greenhouse and subsequent atmospheric escape, it would have had a magma ocean then, which is quite important because the oxygen you leave behind when you break up water can then be dissolved in the magma ocean and react with iron minerals and be taken away, because there isn't a lot of oxygen left on Venus right now. But with 100 bars of CO2, that's not hot enough. It's not hot enough to melt the surface. With 100 bars of water vapor, it is, because water vapor is much more optically thick than carbon dioxide. So, okay, so now in the last 15 minutes, I'm going to talk about atmospheric circulations. The fundamental parameter is something that will be very familiar to you from tropical meteorology. I call it the weak, I call it the weak temperature gradient parameter, but the term weak temperature gradient, the phenomenon of having weak temperature gradients in the tropics, it actually goes back to a paper on tropical balance by Charney. I used it in my thermostat and radiator fin paper, but the whole, the theory, weak temperature gradient theory, was enormously improved and elaborated by Adam Sobel and
Chris Brotherton.
Chris Brotherton, yes, right. Yeah, and it's really at the heart of our understanding of the Earth's tropics. But these planets that I'm talking about, these subNeptunes I've talked about, they're all close enough to their stars that the tidal stresses should have made them tide locked. So that their orbital period is also their length of also gives you the Coriolis parameter. So if you have a planet with a 30-day orbital period, it's like a planet that's rotating. That planet is rotating once every 30 days. So it has a very weak Coriolis parameter. But the relevant number that I like to use in terms of seeing how far you are into this weak temperature gradient regime where you can't sustain large temperature gradients because there's no Coriolis force to balance pressure gradients, or not much. I use the, you can write that as the radius of deformation, square root of the gas constant times temperature divided by the rotation rate of the planet. So this is a global number, so it's a global radius of deformation. And then divide that by the size of the planet A. And so if you have large lambda, you expect weak horizontal temperature gradients. And I go through a more formal scaling analysis applied to tide-locked planets in this annual reviews article with Mark Hammond. But the important thing there is not so much the scaling analysis, which is very close to what other people have done, but there are various ways the weak temperature gradient approximation can break down even if your WTG parameter is large, mainly through generation of nonlinearities. And there are a couple different nonlinearities that can break the WTG approximation. We'll see one of them in the dry dynamic simulations I'm showing you. And so K218b is a very slow rotator, and weak temperature gradients are expected. And in the GCM, that's what we get. That doesn't mean that the dynamics is uninteresting. You have weak temperature gradients, but you still have an important vertical circulation which determines where clouds form. And that is an enormous impact on interpreting the observations. And so most tide-locked circulations around most temperate subNeptunes around low-mass stars, M or K stars, will be slow rotators, tide-locked slow rotators. If you have a temperate subNeptune, meaning that it has a black body temperature roughly Earth-like, if you have one of those around a sun-like star, a G star, it can be probably a rapid rotator. And we haven't explored that regime yet. We don't know of any G star subNeptunes yet because they're harder to detect. But that's an interesting regime to look at. We've been concentrating on the tide-locked regime because there is a big array of subNeptunes around low-mass stars. And you expect them to be in that regime. And this is all subNeptunes, including the hot ones, and there are a few cold ones in there. But most of these are much hotter than temperate subNeptunes, which could have cloud life and condensable water and liquid water in their clouds. There are a lot of them, each of these dots. And actually, if we redid this graph with the latest data, there would be several hundred more of these because there have been 1,000 planets discovered since this graph, and probably at least half of those, more than half of those are subNeptunes,
So
or probable
T,
subNeptunes.
I just
Yeah.
have a quick question.
Yeah.
The T in your scaling parameter, that's a temperature difference, or?
Oh, no, actually, that T is just the,
The
that T is
absolute temperature?
is a kind of mean temperature of the planet. And so,
So why is
and
there
so,
that dependence on the mean temperature?
and so actually, there is some, just like there's a variation between the poles and the equator, just like there's a variation between the poles and the equator and the Coriolis parameter, so you have a different local WTG parameter in the tropics than near the poles. If you have very strong temperature contrasts horizontally, then you could have something that's more in the WTG regime in one part than another. On the other hand, if you are in the WTG regime, the temperature is horizontally uniform, pretty horizontally uniform, and so it becomes consistent. But also, the temperature dependence is just a square root dependence, so it's not a very strong dependence. Now, a more interesting question is actually the temperature varies a lot in the vertical. And so you do get differences in, you actually are deeper in the WTG regime in the interior, deep in the atmosphere where the temperature is high than when you're in the outer part of the atmosphere. So that's another effect. But if you're in the WTG regime in the radiating part of the atmosphere, you'll be in the WTG regime. You'll almost certainly still be in the WTG regime, deeper down if you're deep enough in the WTG regime.
And the
Because it's just a
dynamical
square root
reason for
dependence.
that temperature dependence has to do with like gravity wave speeds, or?
Yes, exactly. It's just it's really just a matter of how far the gravity waves move before they're evened out by geostrophic adjustment. It's all the same stuff that applies to tropical meteorology in terms of weak temperature gradients. Anyway, but so this shows actually my student. This is stuff that was done by my student Hamish Innes. This is the orbital period, and this is the WTG parameter. And if you just estimate the temperature for a zero albedo planet and use that to get the WTG parameter based on the infrared photosphere of the planet, you actually get a nice power law. You actually get a nice power law in WTG parameter versus orbital period. And this whole region is in the WTG regime. That's lambda greater than 1. You're deep in the WTG regime by the time you get to, say, lambda 10. So you see that most of these subNeptunes are going to be in the WTG regime. GJ 1214b has lambda about 1, so it's just you can still support fairly big temperature gradients there, and indeed simulations show that. When you go to temperate subNeptunes with equilibrium temperatures less than 400 Kelvin, then we have quite a lot of those, and they're all sort of deep in the WTG regime. So these K218b simulations I'm going to show you with our with ExoFMS with a hydrogen atmosphere. They're done under K218b conditions. They were done with Hamish Innes, who adopted our model to deal with subNeptunes. The dry case has been published. We're working on writing up the moist case now. I'll just show you a few results from the dry case and then wrap it up. This is a K218b like orbital period, and this is the temperature on. Let's see, what is the? Actually, this is something like the 500 millibar level. Actually, I forgot to put on there what level this was at. But so you can see that you really are deep in the WTG regime. This whole bar is going from 316 to 303. But the only places where you're actually getting a substantial drop in temperature are these near polar vortices. And I mentioned that you can break down WTG if you generate nonlinearities. The particular nonlinearity that allows the temperature fluctuations near the pole is cyclostrophic balance. So you don't have Coriolis, you don't have geostrophic balance because Coriolis force is really weak. But the jets actually get strong enough and the vortices get strong enough near the poles
And this is a
that
snapshot?
it actually generates cyclostrophic balance.
This is a snapshot?
This is just a snap.
So it's like a huge
No,
Kelvin wave?
this is a 10-day mean. So there's a little bit of variability. There's actually not a lot of barotonicity in this flow, and there's not much variability, but there's a little bit. But just to make the graphs look a little bit smoother, there's a little bit of time averaging. Just to allow for lower mass stars where the temperate subNeptunes would have shorter rotation periods. This is a case with a 6-day rotation period. And actually, you see that instead of, these are not mobile vortices. That's a stationary wave that is tied to the fact that you're heating the planet on the day side and cooling it from the night side. So you generate a wave number 1, a Matsuno-Gill type Rossby and Kelvin wave. Okay. It's actually, you don't, at a shorter rotation period, you get more pole to equator temperature gradient, and it's actually much more uniform. I think I'll skip that. But there is interesting dynamics. You generate super rotating jets, and you generate these polar jets. Even with the slow rotator, you generate polar jets. They're not very strong. In the upper atmosphere, they get up to 240 meters. They get up to 180 meters per second or so. But you generate these deep polar jets, and Hamish has shown that these are in cyclostrophic balance. You generate, as is typical for tide lock atmospheres, you generate equatorial superrotation, which is associated with the momentum flux into the tropics that comes from superposing a Kelvin wave and a Rossby wave. These are like the ultimate tropical, Hadley-Walker type circulation. You're heating it on the day side permanently. It's like you made the sun just fixed on, and you have made the sun fixed on one side. So it's like the West Pacific warm pool, but more so because the night side never sees any sun. So you have a huge wave number 1 projection of the heating. And that does give you the waves that spin up this jet. There's also an instability involved in spinning up that equatorial jet, which I won't have time to go into, but we analyze that in the paper. The force balance is cyclostrophic. I'm almost at the end of this now. One of the we analyze, or Hamish analyzed the flow by dividing it up into a rotational and divergent component, which and actually this is in a slightly different coordinate system, where instead of just a lat long coordinate system based on the axis of rotation, it's an axis based on the substellar point. We call that's called the tide block coordinate system, the rotational component. These are essentially those polar vortices you were seeing. The rotational component is dominant, 100 meters per second. The divergent component is only 2 meters per second, but that's what goes along with an upwelling on the day side, an outflow, and a subsidence on the night side, and that has important consequences for where you would be generating water clouds in the night side. You don't generate clouds because you're subsiding and you're dissipating them. I think we're going to skip that. We have a scaling theory for the overturning strength. I don't have time to talk about the traveling.
In the dry case, I guess you heat the surface? That's what you're...
Oh, so there is no surface. So
that's how are you parameterizing the heating?
So we're using radiative transfer. So unlike a case that's heated from below, like the Earth, where you absorb most of the solar radiation at the ground, and then you transmit it upward by convection, here all the heating comes from gaseous absorption of shortwave radiation. And so in fact, given the absorber profile in the atmosphere, you don't actually generate any convection. These atmospheres have no convection. They're statically stable. They're statically stable throughout because the heating is kind of top-heavy and stabilized. That's actually nice because then we didn't have to implement the moist convective adjustment scheme, which is kind of messy.
The radiation directly is influencing the diabatic heating profile that you have.
Yeah, and actually, so all the circulation is in the layer where is in the top 10 bars or so where the shore wave radiation is actually absorbed. And then deeper than that, there's no heating except from what comes out from the interior of the planet. And actually, and based on WTG theory, I'll just mention without don't have time to go into the details. Based on WTG theory, you can actually come up with a nice scaling law for how the strength of that overturning circulation scales with how much sunlight is absorbed, starlight is absorbed. And so these dots are the simulations, and this is the scaling theory. So WTG theory is a really nice handle for capturing what the circulation is doing. No time to talk about the instabilities. I just want to mention one interesting sort of thing from the preliminary results with latent heat. So I mentioned early on that one of the novel features of water vapor in a hydrogen atmosphere is that it has a huge virtual temperature effect because of its high molecular weight. And so that gives you a compositional buoyancy. So that affects convection. In this case, we don't actually have any convection because of the nature of the heating profile. But you still have compositional buoyancy, which gives you a compositional thermal wind. So you have thermal wind due to the gradient in molecular weight if you have variable water vapor because it's condensing in some parts of the planet. And so just to show, this is the 44 millibar latent heat release in the K218b situation, in a K218b-like simulation. And so this is the substellar point there. That's where the sun is beating down, and then over there is the antistellar point. So all the latent heat release is actually, is happening where you have this upward motion at the substellar point in a fairly concentrated region of upflow. But an interesting thing is this is latent heat dynamically feeding back alone. But if you put in the compositional buoyancy effect, it actually shifts, it actually changes the wave dynamics. And it shifts in ways that that's why this is preliminary and not public. You don't understand in detail what's going on here. But it changes the pressure gradients enough, it changes the wave dynamics that this latent heat release is first of all extended and shifted downstream relative to what it is if you just have the latent heat effect alone. So the compositional buoyancy is actually a very big effect in these kinds of atmospheres. And that's where all ended. We're still in the thick. We have a lot of simulations for this case, but we are still diagnosing it to try to understand what's going on. So, and for more about the dry dynamics, the dry dynamics paper is in AppJ letters, and there's this interesting instability, which is part of what's triggering the traveling wave instability, which is part of what's triggering the equatorial superrotation. So thanks for your indulgence in letting me go over a little bit. Thanks.
So I don't know if people need to leave, that's fine. If you have a quick question or two for Ray.
I guess I have a question.
Yeah.
Ray, is there anything we can learn about things like the MJO from considering these weird atmospheres that we might overlook because we have such, primary things going on in the Earth's atmosphere that the secondary things may just escape our attention?
Yeah, so convectively, one reason, it's more likely that it could go both ways. It's more likely that by mining what people have understood about the MJO might give us some ideas about what might be going on here, because we have more observations of the MJO and things like that. But it's also true that when you do these weird cases, it sometimes triggers you into thinking in different
something
directions.
you didn't think about before.
Yeah, and so one of the things that got us interested in these latent heat effects is exactly the question of whether you could get whether in cases with convection you got convectively coupled waves.
Mm.
In this particular planet, you don't get convection, so you wouldn't get convectively coupled waves like I guess some people think the MJO is. But in some ways, it's simpler to analyze because without convection, the relationship between latent heat release and heating is simpler.
Yeah.
You don't have to think about things that trigger convection and things like that. But we're also doing these moist things for planets with a surface in which you could get triggering convection, like the MJO. But,
Thanks.
yeah, John.
Great. Is this work going to lead to the possibility that if you had a hypothetical weather satellite with remote sensing at many different wavelengths of radiation, you would be able to look for synoptic patterns in the wind circulations?
Well, actually, we'll probably, in the foreseeable future, we will not be able to see synoptic patterns per se, but you do actually get information about both variability and east-west structure, because as most of the data we get comes from, in typical observations, comes from when the planet passes in front of the star or goes behind the star. You go behind the star, you block the infrared emission. When you're in front of the star, you block some of the stellar radiation. But if you're good at getting a lot of telescope time, you actually observe the emission from the planet as it goes through its entire orbit. So you actually get to see the temperature, the difference in the disk averaged emission as you look at it from different angles. And what's more, if you look at how the emission changes in the course of the planet going behind the star, you get some information about more information about the structure here. So you do get some information about east-west structure, and if you have many orbits, which most of us can't get telescope time for, but get enough orbits with enough precision, then you can actually look at the difference between one orbit and another, and then look for variability. The models have interesting variability. This planet doesn't have baroclinic instability, but GJ1214b does have baroclinic instability, baroclinic waves, in this very interesting inhomogeneous environment where the static stability changes enormously between the day side and the night side. And so there is interesting variability. One thing that hampers observation of the variability is that mostly, in order to get any data at all, given the noise level, you have to average over many orbits. If you're lucky enough to get many orbits, you have to average over many orbits to beat down the noise to just get a mean signal. But Webb is more accurate, has less noise, and so with Webb we might start to see in a few cases some information about the variability. From the models, we know when it should be there. And there's also information in the nature of the variability. And so it'll be exciting times. The main problem with Webb is that time is, it would be an understatement to say time is like gold. I mean, there's nothing to compare it to. The value of time on the Webb Space Telescope is so enormous that we're lucky to get data for just looking at a couple eclipses. So, yeah.
So this is pretty interesting because the planets that you're showing are, they are in a WTG regime, but I think it's kind of like a different kind of variant of WTG than what we see on Earth, because when you're showing the winds there, it kind of like seems more akin to the solar winds seem to be like more of a cyclostrophic balance with the metric terms.
Yep.
And the momentum equations, where on Earth you can see like an ion of a hurricane that's cyclostrophic, but because of the strong rotation.
That's right, yeah.
Within the hurricane. So I'm kind of hung up on the two cycles that you showed. Like you mentioned that those are cyclostrophic. Are they cyclostrophic as in the metric terms, as in the jets, or are they cyclostrophic because they're just spinning really quickly with respect to a low pressure or some combination?
Yeah, so the vortices themselves are cyclostrophic just because of the wind speed, but there is also a jet there. The jets I showed in cross section, which was a zonal mean cross section. Those involve the metric terms.
So I'm thinking of like how in these like WTG planets, the gill response is just so different that is this more like how a gill response would look in these planets, that it would just turn into cyclostrophic vortices and like really strong metric term driven jets rather than like the semi-dystrophic common winds that you see.
Well, actually there is a gill response there. It doesn't show up very well because it's so WTG that you have to look pretty closely to see the Kelvin wave and the Rossby wave. If you look at slightly faster rotators, it comes out better. But the jets are wave-mean flow interactions driven by the Matsuno-Gill response. So the Matsuno-Gill response is there. But this jet structure, which includes in some cases cyclotropic jets, is driven by is a secondary thing. Now, actually, the equatorial superrotating jet in the deep atmosphere is directly driven by a Matsuno-Gill type response. These polar jets are not driven by wave-mean flow interaction. They're just driven by the fact that there's a Lagrangian mean drift in a Hadley-type circulation towards the pole. So you eventually push your angular momentum close enough to the poles that it spins up enough of the jet to make these jets, which are actually correspond to really tiny little vortices in the polar regions. So
Is this Matsuno-Gill response more akin to the one on Earth, or is it the curvature effect also a result of like the metric?
well, it's actually, it's not really that different from the equatorial beta plane stuff. Now, Mark Hammond, who was my earlier PhD student, he actually worked out the linear. He has a paper in his physical journal where he did the Matsuno-Gill response using full spherical geometry on the for somewhat faster rotators. So you get better quantitative agreement with your GCM if you do the full spherical geometry, but there's nothing dramatic that leaps out at you. Now, one important thing though that's different from the Earth, and this is what was in Mark Hammond's thesis. On the Earth, the wave speed is much faster than the wind speeds in the tropics, and so you get the basic Matsuno-Gill response by linearizing around a state of rest. But what Mark found was that the jet speed, the jet speed in these equatorial superrotating jets, which are driven by the Matsuno-Gill response, is fast enough that it Doppler shifts. It doesn't do much to the Kelvin wave, but it Doppler shifts the Rossby wave, so it changes the phase of the Rossby wave relative to the heat. So the hard part of Mark's paper was actually working out Matsuno-Gill theory numerically for a case around a jet. And so the wave-mean flow interaction generates a jet, but that alters the wave. And in fact, we have an argument that the thing that determines the jet speed is that when the jet gets strong enough, it actually stops the momentum transport into the jet. And so it's not primarily a frictionally determined jet, it's determined by the wave-mean flow interaction. But it's interesting, John Boyd actually had a paper long ago on what jets do to the Matsuno-Gill response. I think he was thinking about stratospheric issues because it doesn't apply to the, maybe actually the ocean. I guess the ocean, you get strong current in the ocean, which affects any sort of response. Yeah, there's a lot of use of our basic GFD that most of us learn in a completely new context. Yep.
Yeah,
Do you
go
have-
ahead.
yeah.
I mean,
So-
people are welcome to leave, so that's.
Feel free.
This was a very interesting question that Norman asked, and then you also mentioned Rossby waves. So I'm just curious, and I'm no planetary science expert, or like I don't know much about it, but I'm just curious like how different the Rossby waves are on such planets as compared to Earth, because there's definitely the Coriolis parameter which would be different here,
Yeah.
and also the waves.
Yeah.
I'm just curious.
Oh, they're just like equatorial Rossby waves on Earth. There's
They're
no
not different?
fundamental difference.
Okay.
Although as you go to smaller and smaller, so this is a forced wave number one situation. You project on more than just wave number one, but it's strongly dominated by wave number one, day side, night side.
Mm-hmm.
So you have forced wave number one Rossby wave. But you change the frequency of the Rossby wave, the intrinsic frequency of the Rossby wave, when you have a low Coriolis parameter, beta gets close to zero, and so your Rossby wave gets really low amplitude, and so that's what's going on here. That's why you don't actually see the Rossby wave in this K2-18b simulation. If if you look in the review article I mentioned here, that we have faster rotators. There you see the Rossby wave very clearly. And you know, they look really a lot like Matsuno-Gill type solutions, except they extend further toward the pole, because these are still slow rotators compared to Earth. So the equatorial regime extends practically all the way to the pole.
Okay, let's thank Ray.
Yeah.